Hi everybody, it's Miss Moran and I'm back to talk to you this week about multiplying with larger numbers. We're going to be multiplying by tens, hundreds, and thousands, also using estimation to right size our answers, and working with a partial product strategy, which is the first step in learning to multiply large numbers. So we're going to begin by looking at multiplying by multiples of 10, hundreds, and thousands. And this is just an extension of what we've already done when we did our place value unit. So students are real quick at recognizing these as our place values, and anytime we're working with just a 10, 100, or 1,000, it becomes very easy. Students will say, we're just going to do 7 and basically add one extra 0 because it's 7 in the tens. We're going to do 7, but it's hundreds, so we're going to need 2 zeros. And then for 7 times 1,000 is going to be 7 into thousands, which is going to have 3 zeros. So once they figure out that pattern, they're able to apply that to numbers that are multiples of 10, hundreds, or thousands, but that are not exactly 10, 100, or 1,000. So what students will recognize is that they can do 7 times 5 and identify this basic fact as 35, but it's not 35, it's 35 tens. So how do we show 35 tens, or 35 times 10? We're going to add that extra 0. So it's kind of like doing, again, 7 times 5 is 35, and then that times 10, because we're breaking up this 50 into 5 times 10. All right, so with 7 times 500, we're really breaking that up into 7 times 5, and then also times 100. So 7 times 5 is our basic fact. That's 35 again, with 2 zeros because it's 3,500. We've talked about how 3,500 can also be 3,500. So we've got our 2 zeros here in our factors and our 2 zeros in our product. So for 7 times 5,000, it's like 7 times 5 times 1,000. And so 7 times 5 is 35. Anytime I'm timesing by 1,000, that's going to add 3 zeros to make that be 35,000. Pretty simple. The only time students get a little confused is when you work with numbers kind of like this. 5 times 4 is 20. But it's not really 20, it's 20 tens, and so 20 tens is going to be 200. This is where students say, wait a minute, that strategy that I just used over here, where when I multiply times my tens, I have 1 0, and times my 100, I have 2 zeros, and times my 1,000, I have 3 zeros. Now I've got 1 0 and 2 zeros, so that doesn't look like it adds up. Well, that's because my basic fact of 5 times 4 is 20, so that 0 is really part of my basic fact with one additional 0. So 5 times 4 is going to be 20, but it's 20 hundreds. So I'm going to need to add 2 zeros for the hundreds, which is 2,000. And 5 times 4,000 is going to be 20 as my basic fact with 3 zeros to make it into the thousands. Okay, so we have a different number of zeros here in my product as I had in my factors, but again, that extra 0 as my basic fact, or as my number, my basic fact that ends in 0, is going to add that extra 0. All right, so we're going to use that to extend to estimation. So we're going to be looking at estimating, and the importance of doing this is not really to get an exact answer or anything like that. It's to make sure that kids have their numbers in the right size or the right magnitude. As students start to multiply some of these larger numbers, leaving out a 0 here or there makes a huge difference in their problem. So we want to make sure that students are in the right size. Are we in the hundreds? Are we in the thousands? Are we in the 10,000s or the 100,000s? So for 6 times 37, we're going to just round this to a very simple number that ends with a bunch of zeros. So again, precision is not so important as making a simple problem that's going to give me the right size. So I'm going to rewrite this as 6 times, and I'm going to round 37 up to 40. 6 times 4 is 24. It's 24 tens, so I need that extra 0 there. All right, for 5 times 321, we talked a lot in our last chapter about making a precise estimate and how if we rounded to the nearest 10, that would give us a precise answer. But for our purposes here, we want it to be easy mental math. So I'm just going to make this into 5 times 300. So I'm just going to round to the largest place possible. That'll give me 15. It's 15 hundreds. So 15 hundreds is 1,500. So again, this might not be exactly what my answer is. In fact, it's going to be an underestimate because this is a rounded up number. Or I'm sorry, this number is higher and I rounded down. but this will still tell me about the right size so that I can catch my mistake if I've made one. And then for 8 times 3,896, we're going to round this to 8 times, we'll round that up to 4,000. Basic fact is 8 times 4 is 32, and that's 32 thousandths. Now, if I wanted to be a little bit more precise, an easy way to do that so that I'm still able to do everything mental math is to do what's called a range of estimates. So I'm going to give myself basically a round down and a round up on this number here. So I could write this as 4 times, this is between 20 and 30, so 4 times 20 and 4 times 30. 4 times 20 is 80, and 4 times 30 is 12 tenths, which is 120. So that means my estimate is going to tell me my exact answer should be between 80 and 120. So this is a little bit more precise than just estimating up here, but this still is very easy for me to do mental math. I'm just doing basically multiples of tens there. All right, same thing here. If I want to do a range, I'm looking at the 684, and I know that that's in between 600 and 700. My round down would be 600, my round up would be 700. 6 times 600 would be 36 hundredths, which is 3,600. And 6 times 700 is 42 hundredths, which is 4,200. My estimate's going to be 3,600 to 4,200, and it's going to be a lot closer to, because I would round up to the 700, it's going to be closer to the 4,200. So this helps me to know when I'm doing my exact answer, it should be somewhere in here and somewhat closer to this. That will help me to catch mistakes, not necessarily to make sure my answer is 100% perfect, but we just want to make sure that if we are making mistakes, we can catch them and go back and look at them. All right, and then we'll make this 9 times 3,000 and 9 times 4,000. 9 times 3 is 27,000, and 9 times 4 is 36,000. So between 27,000 and 36,000 is going to be my estimate. And because this rounds down to the 3,000 and is actually much closer to this, we're going to see our estimate's going to be much closer to this 27,000. So probably somewhere 27, 20, 29, 30,000, not quite that high. Okay, so again, estimates, just using a strategy to help us make sure that we are right sizing our numbers. All right, now is for the fun stuff. All right, parents, this is where you have to be patient with me. We're going to be multiplying some larger numbers here. And I know the strategy that I'm going to show you is probably not something you learned in school, and probably something you're going to say, forget that, let me just show you an easier way to do it. I'm going to just show you the way we always learned it. There's nothing wrong with it, and there is nothing wrong with it. But we're going to start with a different strategy, and that strategy is called the partial product strategy. And there's a lot of value to it. I'll explain that in a few minutes. But I want to show you what we do and how we present this, and why the partial products has a lot of benefit over the traditional regrouping strategy. So when we first present this, we'd say, well, we've learned our basic facts. I know my 4s, my 5s, my 6s, my 7s, my 8s, my 9s. The problem is I don't know my 37 times tables. So if I don't know my 37 times tables, I need to break that up into facts that I do know. So if I were going to break up my 37, I could break that up into place values of 30 and 7. Based on what we just learned previously about multiplying by multiples of 10, this makes this a much easier problem. So we're going to use what's called an area model. Basically, the idea of the length times width model, and or imagining this is an array, only not filled in with squares or circles or something like that. And we're going to label this as 4, basically by a 37. Okay, well, we're going to break up 37 into 2 parts, the 30 and the 7. And then I'm just going to multiply. And now, even though I'm multiplying by a large number, it still is an easy fact because I'm really just using my basic facts. So 4 times 3 is 12, but 4 times 30 would be 120. 4 times 7 is 28. So to get my final answer, I'm just going to add 120 plus 28 and get 148 as my answer. So that involved no regrouping, that involved no steps of, multiply this and put this number up here and do this and do that and stuff that doesn't really make much sense to the kids. It makes sense to say, well, we can break this number up into place values and we can multiply it by facts that we know. All right, we're going to go into a little bit larger number here in the hundreds. So I certainly don't know my 526 times table, so I need to break that up. So think about that as a large array. That is 3 times 526. So how am I going to break 526 up into facts that I know? Well, I can multiply by 500. I can multiply by the 2 means 20, and the 6 is 6. All right, so based on what we just learned previously, multiplying by multiples of tens and hundreds is an easy thing to do. 5 times 3 is 15, but it's 15 hundreds. 3 times 2 is 6, but it's 6 tens, so 60. And 3 times 6 is 18. And then we're just going to add, making sure we keep everything lined up. Okay, 1,578. And here we go. You certainly don't know your 4,239 times tables, but we certainly have a way to break that up and make this a much simpler problem using facts we know and things we can do, all mental math. We're just going to record our mental math. So this is 5 times 4,239. The 4 means 4,000. The 2 means 200. The 3 and then 9. Oops, 30. 5 times 4 is 20. Got 3 extra zeros, so that's going to be 20,000. 5 times 2 is going to be 10 hundreds, which is 1,000. 5 times 3 is going to be 15 tens, which is 150. And 5 times 9 is 45. Okay, students can probably get to a point where they don't even have to line all these up and add them up. They can probably do a lot of this mental math. So 21,195, but I'll go ahead and write all that out. Okay, so one thing that this is really helpful with is teaching students that when they multiply by these numbers, they have to multiply in a certain number of steps, depending on how many place values we have here. So this is going to be a 4-step multiplication problem. This is going to be a 3-step multiplication problem. And this is going to be a 2-step multiplication problem. What a lot of students won't intuitively realize is that this number has to be distributed to all of these numbers. And again, this is what we call the distributive property, where we're breaking up numbers into smaller parts. What a lot of students will want to do is they are thinking about this kind of like they did with addition and subtraction. They think of this as ones place and ones go together, and there are no tens and there are no hundreds here and there are no thousands. So they'll do 9 times 5 is 45. They'll put their 5 down here, and they might even know how to regroup up here. But then they often just want to bring these numbers straight down. They don't realize that this number has to be multiplied by all of these. But doing it with this strategy, it helps them to see that this is actually 4 mini steps of multiplication to solve this problem. Okay, so again, with partial products, here's my plug for why we're going to use partial products. Partial products uses skills that we have to approach more complex problems. So they already know how to multiply basic facts. So we already know how to multiply by tens, hundreds, and thousands. We're going to use what we already know how to do to make more complex problems a little bit simpler. We're going to build number sense, and students are going to be able to multiply doing mental math. This problem, like 37 times 4, they may be out and about and not have a piece of paper, but yet they would still be able to learn how to break that number up into 2 parts and be able to do that with a mental math approach. It makes for a more solid foundation when moving on to traditional regrouping algorithms, so they can see how this relates to, the steps of starting in the ones place and multiplying each one of those numbers as we move across. And it's amazing as we get into this, when I start teaching 2-digit times 2-digit multiplication problems in a couple weeks, how students will be able to take this strategy and almost invent that traditional algorithm on their own. They know exactly how to break up numbers and how to multiply those numbers. This is something that sticks with them, and it doesn't follow a set of rigid steps if you have to do this first and do that first and do that first, like the traditional regrouping algorithm. We will get into that because obviously it is the traditional algorithm for a reason. It is a lot less to write, especially when you get into large numbers, and a lot easier to organize your work, but the steps are confusing. So this will lay the foundation for the steps because the steps are really the same. It's just recorded differently. All right, thank you for your patience today. 15 minutes, but we've got a lot to learn in the next few weeks. We're going to spend about 3 weeks or more on this unit, and so we've got plenty of time to practice our multiplication. All right, thank you for helping out at home.